Okay, so in the previous lectures, we have been looking at propositional logic. We've been establishing new logical equivalencies between propositions. And these propositions have been static, maybe? Like, once you declare a proposition, it's going to be either true or false, right? But what about when there's variables involved, right? So like, what about like something like, what about this proposition? So like, student rank is a data science major. And so this is not a proposition, actually. I said, like, until I put something there, it's not a proposition. But as soon as I put a student's name there, it becomes a true or false statement, right? So this is what we would call a predicate. So predicates and quantifiers. So predicates are just basically propositional functions. That's how I think of them. Okay, so we could say that maybe the abusive of notation, like capital P of X is that. And as soon as we put in an X, it becomes either true or false. Does it more or less make sense, the idea? Yes. Okay, so for notational purposes, I will typically denote predicates with capital letters instead of lowercase, just to distinguish between the propositions we have been doing and these like propositional functions. I need to pin this.
This is the student.
Oh, yeah. There you go. There's a data, and I didn't even finish because I was too busy thinking about that. So it's 80 cents major. So now it's officially a propositional function, it's a predicate. Okay, so what about the question that we could ask for all students in this class, like for all X in this class, this, right? Like that seems like a common thing that would happen, right? Like we need to specify a domain of interest, right? So I need to like write that out probably for you. So for predicates, need to specify a domain of interest. Where can our possible inputs come from? Which students? Yeah. Right. It could be like all UHD students. It could be all students in this class. Like we have to be formal about it. We should specify a domain, just like with any function, right? Like anytime you consider a function in like calculus or pre-cal or something, you have to really consider the domain. What makes sense to plug into it, right? Like if your function is f of x equals 1 over x, 0 is not an acceptable entry, right? So, okay, exactly. So, for a given domain of interest, we might want to check whether or not it's true for all of the elements in there, right? So, I'm going to write this down I'm going to write down the notation before giving you the definition. I want to see if you can guess what it means. And again, I'm not going to tell you anything about, I'm just going to write it out and ask you what you think it means.
Kind of weird.
If you already know, please don't answer. So I need to be a little bit. Oh no, yeah. and I'm kind of not using the best notation here. And if you've been reading your guidebook, you might have encountered this. Okay. So you know these symbols, right? It's the and, right? The conjunction of this. And you know that once you plug in a particular value from your domain of interest, it becomes a proposition, just like we've done before. So whatever this thing is, it's true only when something. Oh, I should have put logical equivalence here. The top one, whatever that is true only when what?
All values are true.
Try to say it a little bit better. You're more or less right, but like just try to say it a little bit better. So this is like your predicate.
Okay.
So each of these is like, so, and this is like something from your domain of interest.
So every time x changes variable, it must remain true.
So I think what you're trying to say is that for all variables in the domain of interest, the truth value of the predicate at that entry is true. And so when the predicate evaluates the true for all values in the domain of interest. So in this case here, right, whatever this is, so not everyone in here, and so if our domain of interest was this class, and this was our P, that top thing would evaluate to be what?
I mean, false.
False, because most of you are CS majors, like only a third of you are data science majors, which means there's at least one case where one of these is false. And then true and false would be, but it's going to be false. It's going to be, you keep on doing the and is only true when they're all true, the conjunction, right? So we don't know what to call that yet, but we know how to read it, right? Like for all. That's actually what this means. This is read for all x p of x. Okay.
It's like an upside down A. Oh.
So yeah, for all x p of x. Okay. Now, what about this one? We don't know what it's called yet, but for this predicate, right, this.
Only one of them is true.
So what would this evaluate to be for this class?
True.
True for this class, because at least one of these, there's at least one data science major in here.
So the E stands for exemplar or
Oh, you're so close. Try again.
exception.
Existence. So this is read here. There exists x p of x. You're on the right track, right? So like using that predicate over there, like we can have, there exists a student in this class such that there exists a student X in this class such that student X is a data science major. This is true. And this statement up here would be for all students X in this class, P of X, or for all students in this class, student X is a data science major, which is false, right? So this is called the universal quantifier. Hold on. Not wrong. It's like foggy today. Ever since COVID, it's been like the worst headache. I'll be all right. I have some Tylenol in my bag. Yeah. So I don't know why I was second guessing something, but yeah. So this is the universal quantifier. Okay. And then this is the existential quantifier. That would be a something else. And this is in Rosen, section 1.4. Right, that's what I was just like waiting for it to happen. I knew it was going to happen. There. I was like, just so foggy. Okay. And these are really the only two quantifiers that we need to worry about. Okay. Now, as far as terminology goes, for the universal, there's one thing to note in that one of the one time where it's false, or the several times where it's false, those would be called counterexamples. So I should probably write that out. So if P of xi is false, then xi is a counterexample to this whole statement. And by the way, even though we're using predicates here, we can think of that whole thing as just a proposition, right? It's a compound proposition over the logical and over the domain of interest, right? Once you pick a domain of interest, this is a single proposition. It's a compound proposition, but it's just like the ones we've been working with. Okay? Yeah.
So in C++, this is just a if statement, right? Or else, like the one is else in the top of
Yeah, I suppose, yeah, you can think of this as just like, if you wanted at least one of the things to be satisfied in order to go into your if statement, it would be this one, right? If you wanted to make sure everything was satisfying some condition before going into the if statement conditional, you do that. Okay. You get like three things to check, it would just be and. And like in Python, you could write a function to check over a set of things like real easy, right? Okay, so are we clear on this? All right. Now, I really need to emphasize something about the choice of domain. I think that this example is a good one. So maybe like Q of x is going to be equal to this. Draw x. Now my proposition, or my predicate is going to be this. Is that, so is this true? Or no, not qubits, sorry. That's qubits. And this is the universal quantifier applied to that predicate. Is this always true? Like, does this evaluate to true? I see a bunch of sad faces.
Is that a 0?
Yeah, it's a 0. So what does this read as? For all x, x squared is greater than or equal to 0. Well, -1 squared is positive 1, right?
Because nothing can equal 0?
Well, 0 squared is 0.
So it's true.
Counterexample. If it's false, there has to be at least one. What is it?
Dang it, screw. It's an
Yeah, you didn't say the main.
There, that's the point. Right? If your x could be complex numbers, then that's obviously false, right? If your x was only real numbers, then yeah, it's true, okay? So you can specify the domain by saying that this is an element of a certain set. And no, we haven't gotten to sets yet, but I'm going to go ahead and introduce the notation because I think it's like you'll get the idea. So for all x epsilon, and then you give like the complex number set. So this just means that x is for every x, it's an element of the complex numbers. It belongs there. And you put your predicate here. This is false. Okay, but if you want to state for real numbers, you can just say epsilon, the real number sign. That happens to be true. Okay. So hopefully that example emphasized the point that the domain of choice is important. Okay.
Just to recap, what does the C stand for?
Complex set of numbers.
Like the square.
Yeah, they could be like real numbers and imaginary numbers. And R is the set of real numbers. Okay. All right. So oftentimes we're going to want to look at negating these propositions, right? Like as soon as I put a domain of interest together with a predicate and a quantifier, I have a single proposition or a compound proposition, but it's just like the things we've been looking at before. So I want to try to pick your brains a little bit and see if some of you can guess what happens when we negate the quantifiers. So if we negate for all x p of x, what do you think that we get?
False.
Whatever x is will be null.
Not for all of P,
Can I say that?
not for all of Px.
So yeah, this reads, it is not the case that for all x p of x, right?
Mhm.
But what is the universal quantifier? What operation does it do a bunch of times? And, right? So let's write it out. So this is the same thing saying not p of x1 and p of x2 and p of x3 and da da da. Right? So what happens now?
Everything has to be false. So the experiment will be true.
Think about the laws that we proved and that we were using.
You don't reuse the other set of laws to be third.
It's the same thing, right? Each of these is just like once you plug in an instance of a student, for example, it becomes a proposition. So this is just like P and P and P and for P and Q and R. So
We have to distribute the numbers, right?
it's not distribution, it's like De Morgan's law. The most important of all the laws that all of the CS majors have to always remember. So what is this going to become? Tell me what to write.
Not P of X.
P and not Q.
So not P of X1 or good catch. Not P of X2, right? Or not P 6, 3. Or dot, dot, dot. Can we rewrite this a certain way? Like, this is or taken over all the things in the domain of interest. What is that? It's okay if you don't see it, but it's something that we just looked at. Or taking over all things in the domain.
Would be ideal.
No, think about what we did today. We saw it earlier. It becomes, yes, the existential. This is, there exists X, not P of X.
Not because it becomes more.
Yeah, we have a bunch of ors now, which is the existential quantifier. So this is like De Morgan's law applied to the quantifier. So we've established one important property, and that is that if you negate the universal, you get the existential of the negation.
Vice versa, right? If you do it-
Well, before I move forward, some of you were thinking about like when it's true, when it's false. I mean, we should probably talk about that, right? Okay, so suppose that if we negate this, like let's just let's just suppose it's true, right? Like we're just supposing that it's true. So that means that whatever's in here, what's its truth value? False, right? If the negation of something is true, whatever's in there must be false.
Right.
So that means that this must be false, right? Which means that at least one of these is false, right? There exists one of them that is false, right? So maybe I should write it out a little bit more clear. So that means the whole thing is true. And it's like we're negating. Like that is that, right?
Yeah.
Okay, so make sure. Which means that all of this is false. Okay. So, but this is the same thing as this, right? So all of this, none of those can be true. Or did we look at it right? What am I saying here? Again,
At least
five.
one of them.
If one of them is false, all of them are false. The whole thing is false.
Yeah, so if at least one of these is false, then the whole thing is false, right? But we're negating that, right? So when we negate that, we get a bunch of ors, right? So let's write it out. So like we have like maybe not, maybe like one of them is true, right? And maybe not one of them is false and not true, right? So, oh no, sorry. Or, yeah, or. And then just keep on going, right? But we know that there's at least one of them that's false, right? So look at what this is saying. There exists one of them such that So there exists x such that not p of x. Right? There exists x, and again, it's true over here, right? There exists one of these, negation is true. Right, so then this thing would be true on this side, which matches up with that side. So now let's suppose it's false. And like I'm trying to emphasize like the language here. So it is not the case that for all x, p of x is equivalent to there exists x not p of x. So now to really emphasize the point, let's suppose this evaluates to false. So then it's like negating
all the truth.
this is true, right? This has to be true. The negation is false, which means that all of that's true, right? Which means that if all that's true, every single one of those is true. And what does this become? This becomes false or false or false or false all the way through. Which means that there doesn't exist one that's going to be true. This is going to evaluate to false. Okay. Just to try to emphasize why this is working more. Okay. All right, so we've established that. And now let's negate the existential. So let's negate there exists x p of x. Well, this is like negating the disjunction of all of these values. So what is this logically equivalent to? Well, we have to apply the De Morgan's law first, right? Okay. And now we have a bunch of ands, right? The conjunction over all the things in the domain of whatever that is. So then it becomes the universal. For all x, it is not the case p of x. And again, this is just more or less a straightforward application of De Morgan's laws. I do have to say one caveat, though, is that we don't necessarily know that we can apply De Morgan's law when we have 3 or more things in there. We've only ever applied De Morgan's law to 2 propositions. But when we start proving things later on, we're going to prove that we can actually do this using a technique called induction. So there is that caveat. Okay. And honestly, I think that I want to stop it there because the next section is long, but more or less the idea behind the Morgan's law, quantifiers, predicates, are you okay with the ideas? It's the same thing we've been doing. It's just now we have more notation to deal with when you want to look at quantifying propositions over a domain or predicates over a domain. So we'll stop here. And I would suggest before next time to read section 1.4 from Rosen. It's a short class, but again, this section every semester ends up being like 30, 40 minutes long. That's just how soon the sections are. Okay. All right, I'll stop the recording now.